Hi, everyone. I think I'm going to get started. How's everyone doing? Whoa, a response. All right, the coffee has kicked in. That's great news. So my name is Tess, and I'm an engineer at a startup called Chain. And Chain is based here in San Francisco, and we build blockchain infrastructure. Let me adjust this. So if you don't know, it's still, okay, thanks. If you don't know what blockchain infrastructure is, don't worry. I'll get into that in a minute. But the main thing I want to talk about today is a system that I wrote called Iago. And Iago is our high availability storage system built on top of Postgres and etcd. And it really is the storage backbone of every system that we build. So here's what I'm going to cover this morning. So first, as promised, I'll give a brief introduction to blockchains and describe the topology of our systems in order to give you a sense of the use case that we're really solving for. And as part of that, I'll give you a little more detail on just what we do at Chain. Next, I'll touch on Postgres and the way that it replicates data before introducing etcd and Raft, which is the consensus algorithm that etcd uses. Next, I'll talk about Iago itself and the algorithm that it uses before discussing how this system behaves in the event of various failures. And because Iago is a work in progress, I'll then talk about some of the changes that are coming to it. And finally, just for fun, I'll tell you why we gave it this kind of cute, goofy name. So first, what is a blockchain? I know some of you may be familiar with blockchains already, but I bet at least one person out there is sitting there like this, which is certainly, this is from like Bloomberg Business Week, I think. But this certainly is how I felt when I first started learning about blockchains. So I do want to give a quick overview. So a blockchain is a ledger where transactions are grouped into blocks and chained together via the hashes of all the data in that block. So in this simplified diagram, at the bottom we have block 1, which is full of all those transactions you can see. And then like chained to it via its hash is block 2, which has all of its own transactions in addition to the hash of that previous block, block 1. And as more transactions happen across the network, they can get grouped into a new block, which we could call block 3, which then would contain the hash of block 2. So this block then gets appended to that ledger. So you end up with this long chain of blocks. Very clever, right? So each block points to its previous block by including that previous block's hash. And this blockchain is that ledger. So when people talk about distributed ledgers, this chain of blocks is the ledger. And then this ledger is shared across every node in the network. So in many blockchains, including Bitcoin, the network comes to consensus about what exactly the next block should be through an algorithm called proof of work, which involves every node in the system racing to find the hash of the current block. If you've ever heard of mining Bitcoin, that's what's going on here. I'll talk a little bit more about consensus algorithms in general later, and there are some really cool things going on with proof of work. But unfortunately, diving deep into mining is out of scope for this talk. And by the way, the word blockchain is a little bit like the word cloud in the sense that it's a buzzword, which like sometimes loses some of its meaning. And if you ask 5 different people what a blockchain is, you'll likely get 5 different answers. So the way that I see it, you could pick maybe 6 attributes. And any system that fulfills 4 or 5 of them could reasonably be called a blockchain. And if I had to take a stab at what those attributes are, I'd suggest the following 6 things. So first, a replicated ledger. In other words, does this system use an append-only log, and is that log replicated across multiple servers? The second attribute is a cryptographic commitment history, used to protect the integrity of that ledger's history. So this, of course, is what's happening when blocks contain the hash of the previous block. They're creating this commitment history that makes it very hard to tamper with without rewriting the entire history. Third, transactions that are authenticated by public key crypto. So when I send you money over a network, do I have to authenticate myself by signing something with my private key? And this idea is really central to Bitcoin and most other blockchain implementations. Fourth, accounting rules. Are there accounting rules about the way that transactions must balance inputs and outputs? So for example, both Bitcoin and the chain protocol use an unspent transaction output model, or UTXO model, to balance transactions. But something like Ethereum, if you've heard of that, doesn't. The fifth attribute is shared access. Is there shared access, either publicly or perhaps just across several organizations? So generally, a single organization has enough internal trust, or should have enough internal trust, that things like cryptographic commitment histories don't really make sense. And finally, proof of work. Do nodes in this system come to consensus through proof of work? Again, proof of work is that algorithm that relies on mining specifically to allow nodes to come to consensus. And Bitcoin uses proof of work because it's resistant to malicious behavior from nodes in the system, like within the system. And so it allows for systems that can be truly decentralized. But it's also very expensive. So processing each transaction on the Bitcoin network can take the same amount of energy that it takes to power an American household for a day. So this is a very expensive way to come to consensus. And again, not every blockchain has all 6 of these attributes. Bitcoin does, but many other blockchains only have 4 or 5. And the chain protocol in particular has the first 5, but not the 6th. So at this point, I've said the phrase the chain protocol a few times, and at this point, you're probably saying, what's that? So let me take a brief detour to clarify what exactly we do at Chain. So Chain has created a blockchain protocol, which in a fit of wild imagination, we named the Chain protocol. And the Chain protocol has a lot of shared DNA with the Bitcoin protocol, but it's been tweaked and optimized for enterprises. And we also created an implementation of that protocol, which we call Chain Core. And we've partnered with a number of financial institutions, including Capital One, Citigroup, NASDAQ, and Visa, and Chain Core powers all of their blockchain products and blockchain experiments, mostly at this point. Meanwhile, we've open sourced what we call Chain Core Developer Edition, which is a complete implementation of that protocol. So the code that we've open sourced contains all of the blockchain logic so that developers can experiment with Chain Core and get to understand the chain protocol and decide if it's the right thing for them to use in their projects. What we didn't open source was the code necessary to safely run this in production. So that is most of our security and scalability features. Those are still closed, including Iago itself. So although most of what we do at Chain is open source, today I am talking about a corner of our system that's closed source. And if I had to succinctly describe what we're building, I'd say we're building infrastructure for permissioned multi-asset blockchains. When I say permissioned, I mean that the networks are closed. You need permission to join them, unlike Bitcoin, which is an open network that anyone can join, right? And when I say multi-asset, I mean that there's no native currency. Again, when I draw the comparison to Bitcoin, there's no like Bitcoin coin on any of our networks. Instead, assets are issued onto the network instead of mined. So like I said, we don't use proof of work. Instead, we use a consensus model we call Federated Consensus. So Federated Consensus is an algorithm that takes advantage of the relative safety of this permissioned blockchain model. And in this Federated Consensus model, there are 3 types of nodes. So a single node is the generator. And the generator is responsible for receiving transactions from the network, filtering out transactions that are invalid, and periodically aggregating these transactions into blocks. It then sends these proposed blocks to the signer nodes. The signer nodes are responsible for validating all of the transactions in a block and ensuring that there isn't already another block at the same height. So if this block passes validation for a given signer, that signer will add its own signature before sending the block back to the generator. The generator will then publish the block to the network once it's received M of n signatures, where M and n are specified by a network-level consensus program. So n is the total number of possible signatures, and m is the number required. And the generator can also be a signer node. And then in this system, all other nodes are simply what we call participants. They can verify and validate blocks and transactions if they want, but their approval isn't required for the blocks to be published. The system can proceed even if they don't like what's going on. So you might visualize that like this. Here's a very graphic or richly graphic representation of a blockchain network with a single generator, a couple signers, and the remaining nodes are participants. So federated consensus is pretty safe. It guarantees that we won't have conflicting blocks, which is to say it guarantees that nodes will be able to come to consensus, assuming that no more than 2 m minus n minus 1 signers violate the protocol or misbehave. So for a 3 of 4 network, 2 signers would have to misbehave before the protocol fails. And signers can misbehave in 2 ways, either by signing and validating invalid blocks or by refusing to sign a valid block. These are both ways that things can fail, but as long as no more than 2 m minus n minus 1 signers misbehave, we can proceed safely. And this protocol also, or the chain protocol in general, supports consensus improvements. So we could implement a more paranoid consensus algorithm if we needed to. So federated consensus is more efficient than proof of work, which is important, right? But it does rely on the assertion that the generator and at least m of those signer nodes must stay online. So they have to be robust and highly available. Again, this is different from a system like Bitcoin where there are many nodes that can create a block. Bitcoin has no availability requirements for any particular participants. In a system like Bitcoin, each node is a single server. So in that environment, when we talk about distributed systems, when we talk about fault tolerance or consensus, we're really looking at networks at this level. And so far today, I've talked about consensus at this level. But now I want to drill down and take you into the internals of a single node. Because when chain networks are running in production, each node contains its own little distributed system for maximum fault tolerance. So this roughly is the anatomy of a single node. A single node can contain several servers, each running core D, which is the core daemon that runs all of the blockchain logic. And off to the side, on the very far, I guess on your right, is signer D, which is responsible for talking to the HSM, or hardware security module, which securely generates and stores private keys and uses those keys to sign blocks and transactions. Now, this section down towards the bottom is really the meat and potatoes of what I'm talking about today. So each core D server has a fleet of replicated Postgres instances. So in other words, for a given core D, each Postgres instance has a copy of all the data on every other instance. So now let's talk about that storage layer itself, beginning with our primary data store, Postgres. So we chose Postgres as our database because it's reliable and well-established, and lots of engineers are familiar with it. There's a pretty good community, and also because it has really great replication features. So Postgres transactions can be replicated between a primary database and a secondary, both synchronously and asynchronously. So in synchronous replication, the primary won't commit a transaction until the asynchronous replica has, in synchronous replication, the primary won't commit transactions until the secondary has received and committed and acknowledged them as well. But in asynchronous replication, the primary will commit them as soon as it receives them. So by default, Postgres replicates asynchronously. This is more performant, but there's a higher risk of data loss, right? The primary could commit a transaction and then fail before the secondary has actually committed it. So for our data layer, we want to combine these two replication modes. We want core D to write to a primary, which will synchronously replicate to a secondary, which in turn will asynchronously replicate to a tertiary. We could call these instances A, B, and C. And we could also add instance D, which would asynchronously replicate from C, and E, which would asynchronously replicate from D, and so on and so forth. So we could have sort of this infinite, well, in theory, infinite line of asynchronous replicas if we really wanted. If our primary A dies, we want core D to start writing to the sync rep B, which will then become the primary. And C can move up to become the new sync rep. D would continue to asynchronously replicate from C, and so on and so forth with our, again, theoretically infinite long line of asynchronous replicas. In practice, there's usually 3 instances. If there are fewer than 3 instances, this is considered a degraded state, and an operator has to intervene. So this is still a safe state. In this configuration, like the one that I have on the screen, we're not going to lose any data. But if we only have 2 live instances, we can't recover if another peer goes down. Okay, so now I'd like to take a step back and talk about Iago itself and the algorithm that it runs to coordinate this fleet of Postgres instances. Iago uses an algorithm from Joyent's Manatee project. And that is an ASCII Manatee. I borrowed him from the Manatee project's README, and I think he's actually in every source file they have as well. So there's strong branding from the Manatee project. And Manatee is a high availability Postgres project that uses Zookeeper and is written in Node. And my team really liked the algorithm, but we were less excited about operating Zookeeper or managing a service written in Node, especially since we don't use Node for anything else. So I re-implemented the algorithm in Go, which is our language of choice. Core D and most of our other services are written in Go. And I also swapped out Zookeeper for etcd, and the resulting system is called Iago. If you're here today, I'd be shocked if you weren't familiar with etcd, but just in case, I will say it is a distributed key value store built by CoreOS that uses Raft as its consensus algorithm. And Raft isn't Byzantine fault tolerant, so that is to say it's not resistant to malicious behavior coming from inside a network. And of course, this would be a problem for something like Bitcoin, where anyone can add a node to the network. But in this particular case, Raft is perfectly safe because it's being used inside a single node, so which is just as permissioned as our whole system, obviously. So Raft was created to be a more understandable version of Paxos, and the paper that introduces it is not at all shy about this. In fact, it contains this sort of amazing quote about how difficult Paxos can be. We struggled with Paxos ourselves. We were not able to understand the complete protocol until after reading several simplified explanations and designing our own alternative protocol, a process that took almost a year. So Raft really tries to take the consensus problem and make it more understandable. So it tackles this by breaking the consensus problem down into 3 relatively independent and relatively simple subproblems. So if we think of the consensus problem as a sort of question like, how do we ensure multiple nodes apply state changes in the same order, we could break that question down into 3 smaller questions. So first, there's the question of leader election. How does a new leader for the cluster get selected when the old one is unavailable? Second, there's the issue of log replication. How should the leader accept log entries from a client and then replicate them to other nodes in the cluster? And finally, there's the issue of safety. If any node has applied a log entry at some index, then no other node can apply a different entry at the same index. So when we break down the general consensus problem in this way, it suddenly becomes much more tractable. The nuances of how Raft solves these individual subproblems are quite interesting, and they do some actually very clever tricks, often in service of understandability, which I really appreciate. But alas, the details of all of that are also out of scope for this talk. Okay, so let's come back to Iago itself. Just a second. All right, so let's examine the internals of a node in an Iago cluster. So each Iago peer contains 3 things. It runs a Postgres process, an etcd process, and then what we call the sitter daemon, which owns the Postgres process and is responsible for knowing what this peer's role is and for promoting this peer if necessary, so from async rep to sync rep or from sync rep to primary. So in other words, the sitter is the daemon that's responsible for running that algorithm from Manatee that I mentioned earlier. So let's dig into that algorithm itself. When a new peer comes online, the first thing its sitter daemon does is register itself with etcd. So it creates an ephemeral representation of itself with a configurable timeout, and it refreshes that representation halfway through each timeout. So the key thing here is that if the node goes offline, its ephemeral representation will disappear too. With that in mind, each node's ephemeral representation is watched by another node's sitter. So the primary system monitors the sync rep and all of the async reps, and the sync rep monitors the primary. So if any of these nodes go offline, their ephemeral representations will disappear from etcd, the monitoring sitter will notice, and then that monitoring sitter will take action to restore the entire Iago system. Whenever an Iago peer makes a change to the system, it does this by modifying the cluster state. The cluster state is stored in etcd, so everyone agrees on it, and by design, it can only be updated by the primary, or by the sync rep if it's about to become primary. And every peer in the system checks the cluster state to know their role in the system. So the cluster state includes unique identifiers for the primary, the sync rep, and all of the async reps. And it also includes an integer for the generation, which identifies the cluster state. So if a peer changes anything in the cluster state, aside from the list of async reps, it must increment the generation. This prevents collisions. I'll demonstrate how this comes in handy shortly. Cluster state also includes the position of the write-ahead log from Postgres, recorded at the time that this generation was declared. So keeping track of the wall can be used to prevent data loss during certain edge KC events, and I'll also get into that in a little bit. So to dig into this algorithm, let's look at some of the code executed when a peer is running a sync rep. When the sync rep runs its monitoring loop, it's checking for 3 things. First, it's checking that the primary is still online. If it notices that the primary's ephemeral representation has expired, it will go ahead and promote itself to primary. Second, this peer is checking for a change in generation. If the generation has changed, that means that the primary must have made a change to the cluster state, and this node needs to check its role. Finally, in this monitoring loop, the sync rep is running a health check on its own Postgres process. So if this peer's Postgres process fails, it will take itself offline, signaling to the primary that it needs to promote a new sync rep. Before we dive deeper into internals, I want to take a step back and point out how Iago looks from the perspective of CoreD, our application server that runs all of the blockchain logic. So when CoreD goes to query its data layer, it doesn't have to step through a complex web of Iago logic. It doesn't talk to the sitter at all. On startup, it simply asks etcd for the IP address of the primary Postgres process, and then queries that process directly. If CoreD ever can't reach the process, because, for example, that process has gone offline, CoreD can simply re-query etcd for the latest primary. So this interface is actually pretty simple. Okay, so let's dive back into it. So I'd like to really illustrate how this works by showing you what happens when something goes wrong. Okay, so let's look at a scenario beginning with a very basic cluster state with 4 databases and a primary A, a sync rep B, async reps C and D at generation 1. So what happens if the primary goes offline? By the way, I was like so excited to actually have a use case for that keynote animation. Like the most exciting. Oh, thank you. Should I do it again? Anyway, okay, so the first thing that happens once the database has gone up in flames is that the primary's ephemeral representation will disappear. So you can see I gave him a little skull in the ephemeral node list. So the sync rep will then notice that the ephemeral representation has expired. So the sync rep will declare itself primary. So first, it will promote its Postgres process, which is to say that it will reconfigure Postgres so that it can receive writes instead of replicating. And next, the sync rep will rewrite cluster state. So now the cluster state shows that this node B is the primary, the first async rep is now the sync rep, and the generation counter has increased. And of course, at this point, CoreD can't connect to A anymore. So CoreD will query etcd to find the new primary and connect to B instead. Meanwhile, C will notice that the generation has changed and check cluster state to see its new role. It will notice that it's now the sync rep, and it will reconfigure itself accordingly to act as the sync rep for B. So we end up with that state that we were hoping for if we have to failover. This is what we want. Okay, so let's look at another scenario. What happens if the sync rep goes offline briefly and then returns? As before, once the sync rep goes offline, its ephemeral node will disappear. The primary will notice this, and then it will rewrite cluster state in order to promote a new sync rep. So note that the sync rep, async reps, and generation fields have all changed. So now A will start replicating to C, and C will reconfigure itself to be the sync rep. But now let's say that B comes back online. It will notice that the generation has changed, so it won't be able to rewrite cluster state, even if it sort of got into some split brain scenario and thought it needed to declare itself primary or something like that. So instead, it will just recreate its ephemeral node, and when the primary notices, it can bring B back online as an async. So once again, we end up with a totally safe state. Okay, so finally, I want to look at a somewhat hairier failure case. So let's imagine that the primary, which again, we still can call A, receives a transaction from the client and forwards that client to the sync rep. The sync rep commits the transaction and acknowledges it for the primary. And then the primary acts it for the client. Meanwhile, the connection between the sync rep and the first async, which we keep calling C, somehow gets disrupted. So the sync rep fails to send this transaction to that async rep. In other words, we're now in a place where the client believes that the transaction has been accepted, but none of the async reps have actually committed it. So now let's say primary A goes offline. This triggers a new generation, with the old sync rep B as the new primary and the old first async rep C as the new sync rep. So I'm kind of skipping over some of the animations here, but I assume you can still follow along. Okay, so we're here. And now let's say that this new primary B goes offline as well in short order. So this leaves us in an uncomfortable position. What happens to that transaction? The client thinks it's been committed, but the database, that is database C, that is supposed to become the primary, hasn't actually committed it. So fortunately, we have something in place to catch this very issue. So remember how we store wall position in cluster state? That value represents the position of the wall at the beginning of this generation. So whenever a sync rep is about to promote itself to primary, it first has to check the wall's position against, it has to check its own wall position of its own Postgres storage against the wall position stored in cluster state. And then this node will only be allowed to promote itself to primary if its wall position is larger than that of the wall stored in cluster state. Otherwise, Iago will stop, and an operator will have to intervene. So obviously, we'd rather not get to this state, but as always, it's better to halt a system than to lose transactions. Okay, so with that in mind, let's take another look at that hairy failure case. And this time, we'll keep an eye on that wall position. Okay, so let's say we start in a generation with a wall position of n stored in cluster state. Now, as before, the primary A receives the transaction, forwards it to the sync rep acts it, and both databases commit it, and notably, both A and B's wall positions increase to n+1. And when the async rep C fails to receive that transaction, its wall position remains at n. Then, as before, the primary A acts the transaction for the client before going offline. So now when the sync rep B tries to declare a new generation in which it's the primary, it first checks its wall position against the wall position stored in cluster state. Since the sync rep has a wall position of n+1 and the cluster state has a position of just n, this is safe to do. So database B can now declare a new generation in which it's the primary and C is the sync rep, and importantly, it sets that wall position in cluster state to n+1. So now when the primary B goes offline, C will try to become primary. But when it checks the wall position stored in cluster state, it will realize that its wall is behind. That is, database C has a wall position of n, while the cluster state has recorded a wall position of n+1. So at this point, the system stops and an operator has to intervene. And again, this isn't the most pleasant solution, but it's the best way to handle this particular failure case, which is pretty rare anyways. Oh, oops, I think I have some animations to catch up on here. Goes out, checks cluster state, all right, can't do anything, halts, great. Okay, so having dug into that, I want to talk a little bit about the work that's ongoing in this system. So I started working on Iago about a year ago, and then I stopped working on it, and then I started working on it again, and that's really due to one big thing that started happening recently. And that thing is that we started doing production deployments into our partners' data centers. And what we discovered very quickly is that for on-premise deployments, operational complexity is much more expensive than code complexity. So that is, the operational costs of installing and maintaining dependencies are actually larger than the costs of developing and debugging new code. When I say cost, of course, I'm not just talking about money. I'm talking about like general pain. So we set a new goal of basically minimizing the number of Unix processes that need to run at once. So this, again, is what the relationship between Core D and Iago looks like currently. We have a cluster of servers running Core D, talking to an Iago fleet, where Iago runs 3 processes: etcd, the sitter, and Postgres. And if we consider our goal of reducing the number of different processes, there's really only one candidate for removal. We can't remove Core D, since that's literally the bread and butter of what we do, and we can't remove Postgres, or at least we can't remove Postgres very easily, perhaps in the future. It'll be on the chopping block too. Anyway, we can't really remove the sitter if we have Postgres. But actually, we can remove etcd. So we don't need to be running a bunch of independent etcd processes. We just need to be able to query some highly available, highly consistent service, which frankly is what we want Core D to be. Okay, so at this point, you're probably saying, why would you do that? Are you out of your mind? etcd is great, solves all kinds of problems. We love etcd. I agree. But fortunately, the good people of CoreOS have come through for us once again. So we took the Raft package from etcd and moved it into Core D. So remember, Raft is that consensus algorithm that etcd uses in order to maintain consistency across its nodes. And the folks at CoreOS have written a really great Raft implementation that people can use sometimes without the extra tooling and storage that etcd provides. So in this case, the idea is that all the Core D servers can actually just run a consensus round amongst themselves, and the Iago sitter can query back to Core D in order to do things like read and write cluster state. So our application server now has routes that do normal application logic kinds of things, like creating assets and building transactions, but it has a whole set of Raft-specific routes as well. So it has a route for new nodes to join this Raft cluster, for example, and a route for nodes to communicate Raft state changes. And this work isn't done yet, and there certainly is tooling from etcd itself that we love and miss and are going to have to, like, at least minimally replicate. But the prospect of not having to maintain this extra dependency inside of someone else's data center should be totally worth it. We also get one more nice benefit from this, which is that we can now put other data into this Raft storage system too. So we looked for data that needs to be consistent but doesn't get written often. And it turns out that the configuration state for Core D, which is stuff like, is this node a generator, is it a signer, so on and so forth, that data is really a prime candidate for this. And this work is very much ongoing. So I only recently merged this PR, and as you can see, when I made the slides, it was still open. And all of this work of incorporating Raft is public. So if you want to check it out, you can. Okay, so finally, as promised, I wanted to share why I named this project Iago. So obviously, the single most important consideration when naming a project written in Go is including the word Go somewhere in the name. Thank you for the chuckle. But I also liked Iago because it's short, and because Iago is a Shakespearean character from Othello, who goes around telling different lies to like every other character in the play. So he lies and creates chaos, and so this name is sort of aspirationally ironic, because our Iago should create harmony and truth by telling every node in the system the same thing. Okay, so that's about all I've got. I think I have a few minutes for questions. Before I open it up for questions, I do need to mention that, of course, Chain is hiring. So if you get excited by this kind of thing, if you're interested in consensus algorithms and distributed systems and storage, please come talk to me or shoot me an email. I'll be around all day. Okay, so that's all I've got. I think I have a couple minutes for questions. Or we can go to lunch, you know, your choice. I think there's a mic going around.
I had a question regarding the latency between the actual state of the network. Can you hear me still?
Yeah.
The question is around the latency between the actual state of the network and its representation in etcd. So is there a scenario where your application assumes that the database is available and it can't reach it?
Sorry, what was the very last part of that? Right, so if it can't actually reach the Postgres process and receive that like acknowledgement from the primary, which can only happen if both the primary and the first replica receive it, it will like consider that like a failed transaction. So it will have to requery etcd to find the location of that Postgres process. I mean, in practice, it hasn't been a problem.
Awesome. Thank you for the talk. I wondered if there were future plans to open source Iago.
Yeah, so perhaps. I think part of it depends on sort of like how, like I said, it's a bit of a work in progress, and some of it is open source and some of it isn't. From a business perspective, it falls like pretty thoroughly onto the side of like production safety that we are trying to sort of hold close to our vest. Is that the phrase? But definitely part of it is open source already, so it's possible in the future. That said, if you like it, the Manatee project, which I mentioned, is totally open source. There's some really great design docs. Like, I totally could only do this because their design docs were so thorough. So if you're interested in that kind of thing, they're a really good resource.
So first, real credit to you for doing that kind of work, doing distributed databases.
Thank you.
Securely is very, very challenging work, as I know from experience. I'm curious though why you and the company decided to embark on doing that versus using a database, say like Cockroach, which is also in Go and is also distributed and replicated.
Yeah. Yeah, I mean, I am a big fan of Cockroach for sure. And again, they are another source of like knowledge and inspiration for a lot of work we're doing. At this point, the primary, so when we started building the system, Cockroach wasn't really a viable option yet. They only recently, I think, had their 1.0 release, like two weeks ago, something like that. So they weren't really an option as our primary data store at the time. Otherwise, we might have chosen them. At this point, like we really are guided by this fact that operations are so painful to do like in someone else's system, that the fact that like if we were going to move off of Postgres and onto another thing, I think Cockroach would be a really strong candidate. I think it's actually more likely at this point that we move to something embedded and drop Postgres. So I sort of winked about this in my actual talk, but we're investigating dropping sort of like non-embedded databases altogether and moving to something that's completely embedded inside of Core D.
So along those lines, two questions really. It looked like you were using etcd version 2 rather than
Yes.
etcd version 3.
That's right.
Is there some reason for that, or is that just timing?
Just timing. We haven't gotten around to.
And the other part of that is, did you consider at all just simply embedding etcd itself in the binary? If the problem administratively is actually the process, then what's the problem with just embedding etcd within your binary for Core D?
Yeah, I don't know actually. I'd like to talk to you more about that afterwards. Should we go to lunch? Okay, thank you.